Hey everybody, this is Math Adventures, and today I want to show you a really cool function that uses whole numbers and flips them over, and I like to call it the number flipping function. And as you can see here, I have the number 12,345. This function should turn that formula should turn it into 54,321. You might be thinking, how on earth is a formula going to do that? I've never heard of anything like that. Well, I haven't either, which is why I think it's kind of cool. But there are two things that you probably have to know before we take a look at this function, and they're some really simple operators. Let's take a look at this one, mod 10. What mod 10 does is it gives you the remainder of the number after you divide it by 10. So for example, 28 mod 10 would just be 8, because it's 2, remainder 8. An easier way to remember mod 10 is just whatever's in the ones place for a whole number, that's what mod 10 is. 56 mod 10 is 6, 108 mod 10, 8, and so forth. Next one you got to know is this one. They call it the floor function, greatest integer function. There's various names for something like this. But what it does is it takes whatever number is in there and it gets rid of whatever extra decimal that you have and just takes it down to its whole number. So for example, 4.9, floor of that would be just 4. Floor of 5.2 would be 5. It kind of makes sense, right? You're going down to the very bottom of that floor. The way I remember that is in a building you can't be in a 4.2 floor or a 5.6 floor. That's just ridiculous. You're on a 4th floor or 5th floor or 6th floor, whatever. So here we go, mod 10 and the floor function. And those are really the toughest things that you really have to use in this function. It's not that bad. Let me show you how this function works with a 4-digit number. And the reason I choose the 4-digit number instead of something easier like a 2-digit or a 3-digit is, yeah, those others are easier and shorter, but you'll end up having to do more work just because it's harder to see the patterns that happen with a 2-digit and with a 3-digit. When we have a 4-digit, it's nice and easy to see all the similarities and stuff, and you'll see what I mean in a sec. Let's just hop right into it. 5,632, I believe the number was, and we want that to be 2,365 at the end, right? Well, the way I thought about it was we're not really doing anything to the number as a whole. Rather, we're taking each of these terms, the 2, the 30, the 600, the 5,000, and we're doing something to them to turn it into another number. The 5,000 turns to 5, the 600 turns to 60, the 30 turns to 300, and so forth. So let's start off trying to pick up, I don't know, just the first number, the 2,000. How could we get access to this 2? Well, I already explained the mod 10. This number, mod 10, is just whatever's in the ones place. It's just 2. So this quantity right here is 2. Well, you can take that quantity, and since we want 2,000, multiply it by 1,000. Alright, that seemed easy enough. We picked up the first number. Let's see if we can pick up the second number, and hopefully it'll be in a similar way to this. So we want to pick up that 3. We want that to be a 300. Well, we could divide by 10. That gives us 563.2. We don't care about the decimal, so we can just take the floor of that. That gives us just 563. If I do that mod 10, I take 563 mod 10, and that'll just be 3. That whole quantity will just be 3. And since we want that to be 300, the next number in our number, I guess, just be times 100. Okay, great. Let's see. That was a pretty similar way to the first way. Let's see if we can keep this train just rolling. Let's see if we can't get that 6, turn that into a 60. Okay, divided by 10. Maybe if I divide by 100, I get us somewhere. I'll get 56.32 if I divide by 100. I'll get 56 if I take the floor of that. I'll get 6 if I take that quantity mod 10. We want 60, so I take that whole thing, it's 6 times 10. Okay. See, we're already almost there. See how we're adding all these things together to get our 2,365? Let's see if we can't get that last number. It shouldn't be that bad. The first 3 weren't. Divide that by 1,000. Sure. That'll give us 5.632. taking the floor of that will just give me my 5, all I really care for. And at this point, I could really just stop. I already found my 5. But it's really nice to continue these patterns right here so that when we write a formula, we're able to take a look at the patterns a lot easier so that it applies to all the numbers in all the cases. And, divide by 1,000. So, let's see what happens if we do mod 10. Well, this number will just be 5, right? And 5 mod 10, like I said earlier, single digit numbers mod 10, just that number, so nothing has really changed. And everything out here is multiplied by something. 1,000, 100, 10. Well, this is 1. I mean, we've been just getting 10 smaller each time, so. And if we multiply by 1, we haven't changed anything. And now you can see how all these terms follow the exact same form. Not this one, actually, but we can make it, right? Let's divide by 1,000, 100, 10, let's divide by 1. That doesn't change anything about what we had before. Let's take the floor of that. Since we had a whole number, the floor doesn't change anything either. So I just added these right here and that 1 for show, pretty much, you could say, because I wanted to continue this pattern. But it's important to have that show because now, if I did this just with 2 numbers, you might not have seen the pattern. But now that I have 4 things that we added up, you can clearly see we have a quotient here divided by some power of 10, and we have mod 10, and then multiply that whole thing by some power of 10. So now I'm going to try to generalize this or write this into a formula that applies to all the whole numbers. I'm going to keep one of these terms just so you can see the structure, what form we're going to follow for this number. Notice we had a 4-digit number and we added together 4 different terms. So, if you're not familiar with this, that's quite alright. But when we add things together, a lot of the times we use something called a sum, and we use sigma to signify that. If we had a 4-digit number, we would add up 4 terms, but let's just, if it applies to everything, if we have an n-digit whole number, we add up to n terms. And we start on our first term, and for my index, I'm just going to use 1, right? So we're counting up the first term to the nth term. And let's think about the form that all these things followed. We had the floor, right, of x divided by some power of 10. In this case, this was the last term we added, so we want the first term to be divided by 1, which is 10 to the 0 power. Well, if I write 10, our first term we want to be 10 to the 0 power. Well, our first term is going to be k equals 1, so if I do k minus 1, if I do k minus 1, gosh, darn it. There we go. If I do k minus 1, that should equal 0 for my first term. Next term is going to be k equals 2, so it should equal 1 for my second term, and so forth. It should be getting bigger, right? We were dividing by bigger and bigger powers of 10. And then we took that quantity, mod 10, right? That's all of them had a mod 10 after this floor function here. And we always multiply it by something, right? And hopefully you notice that here we divide by 1,000, multiply by 1. Divide by 100, multiply by 10. Divide by 10, multiply by 100. So one of them is small and one of them is big, and they're going kind of opposite directions, you know. One of them's growing, one of them's shrinking. So in this case, we had 10 to the 0 power first. Here we're going to want to have 10 to the 3rd power first. And in this instance, or by 3rd, that was that specific case. But if this is to the 0 power, how can we write to the 3rd power here? In our case, we had 4 digits. So let's do n. But it was to the 3rd power, so we just subtract k, right? Because that means that for our first term, we're going to have, as the exponent, we're going to have 4 minus 1, which is 3. For our second exponent, we're going to have 4 minus 2, which is 2. 4 minus 3, which is 1. 4 minus 4, which is 0. And those are all the powers of 10 that we had. And if you take a look at that, it doesn't look pretty. If it was all in one line, it might. But yeah, that function right there, this formula right here, takes your whole numbers and it flips them over. It works for single digit, 2, 3, 4, 5, any digits you want, whole numbers. That's amazing, isn't it? I think that's pretty cool. You can use this to program a computer, tell you to flip an integer, anything you want. So anyway, try to give this a cool name. I like calling it a number flipping function, but that's kind of weird. Or, I don't know, hokey, unoriginal. Anyway, thanks for watching, and talk to you later.